Last time we ended on a promise. We'd spent a whole conversation rebuilding mechanics around the principle of least action, the idea that nature picks the path that makes a quantity called the action stationary. And right at the end, you dangled something almost outrageous. You said the reason energy is conserved, the reason momentum is conserved, the reason any of these great conservation laws hold at all isn't a set of separate lucky facts about the universe. You said they all come from a single deeper idea, and that idea is symmetry. George, I've been sitting with that for a while, and I want the whole thing today. Why on earth would "the universe has symmetries" tell me anything about what's conserved?
Because it's one of the deepest bridges in all of physics, and the person who built it is someone everyone deserves to know. Emmy Noether. What she proved, around 1918, is a theorem so central that once you see it, you can never look at a conservation law the same way again. In one sentence, for every continuous symmetry of a physical system, there is a corresponding conserved quantity. That's it. That's the whole engine. Symmetry on one side, a conservation law on the other, locked together exactly. Not approximately, exactly. And by the end of today, when I say energy is conserved because the laws of physics don't care what time it is, I want that to feel not like a slogan, but like something you could almost have derived yourself.
Okay, but let me slow you down immediately, because you used a word that sounds ordinary but I suspect isn't. Symmetry. When I hear symmetry, I think of a butterfly or a snowflake, a shape that looks the same on both sides. That can't be quite what you mean when you say the universe has a symmetry.
It's a beautiful place to start, because your butterfly is exactly the right instinct. You just have to generalize it. Here's the precise idea a physicist means by symmetry. A symmetry is a change you can make to a system that leaves something important unchanged. With the butterfly, the change is reflect it left to right, and the thing left unchanged is its appearance. So symmetry is always a pair, an operation you perform and a quantity that doesn't notice. Now, in physics, the thing we demand not notice is not the appearance. It's the physics itself. And more precisely, as we'll see, it's the action, that quantity from last time. If you can do something to your whole setup, move it, rotate it, wait a while, and the physics plays out by exactly the same rules, then that operation is a symmetry of the physics.
So the operation might not be a reflection at all. It might be something like slide the entire experiment 3 feet to the left.
That is precisely one of the great ones. And let's make it the first of 3 headline examples, because 3 examples will carry the entire theorem. Imagine you do a careful physics experiment, say 2 carts colliding on a track, here in this room. Then you pick up the whole apparatus, carry it over to the other side of the building, set it down, and do it again. Same result. The carts don't behave differently because they're now near the window instead of the door. Space itself doesn't have special favored locations. One place is as good as another for doing physics. Physicists call this the homogeneity of space. Space is the same everywhere, and the operation that expresses it is translation, sliding everything over by some amount. That is a genuine, continuous symmetry of the laws of physics.
You keep saying continuous, and last time you leaned on that word hard too, when you were careful to say stationary instead of least. I take it continuous is doing real work here, not decoration.
It's doing essential work, and it's exactly the hinge Noether's theorem turns on. So let's nail it. A continuous symmetry is one where the operation can be done by any amount, including an amount as tiny as you like, smoothly, with no jump. Sliding everything over, you can slide it by a mile, or a foot, or a hair's breadth, or a millionth of a hair. There's a smooth knob, and every setting of the knob is a symmetry. Contrast that with your butterfly's mirror reflection. You either reflect it or you don't. There's no such thing as reflecting it a little bit. That's a discrete symmetry, all or nothing, no knob. And here's the crucial fact. Noether's theorem is about continuous symmetries only. The smooth knob is what lets you do a sliver of the operation and track what happens. And that tracking is what hands you the conserved quantity. Discrete symmetries, like mirror reflection, are deep and important, but they give you something different. They don't hand you a conserved number in this way. So, continuous, smooth knob symmetries are the ones that pay out conservation laws.
Good. Continuous means there's a dial you can turn by any amount, and every setting leaves the physics alone. So back to sliding the experiment across the room. That's a continuous symmetry. Space is the same everywhere. What does Noether say I get in return?
You get conservation of momentum. Linear momentum, mass times velocity, the quantity of motion, is conserved precisely because space is homogeneous, because you can slide your experiment anywhere and the physics is unchanged. Let that land because it's startling. The reason a rolling cart keeps its momentum, the reason momentum is conserved in every collision anyone has ever measured, is not some separate law of carts. It's a shadow cast by the fact that space has no special places. Move the symmetry knob, translation in space, and out the other side of Noether's theorem falls momentum, conserved. One down.
Before we go on, walk me through it in an actual collision, because momentum is conserved is a phrase I memorized in school without ever once feeling why it should be true.
Let's do exactly that, because it makes the abstract link tangible. Picture two carts on a long straight track. They roll toward each other, collide. Maybe they bounce, maybe they stick, doesn't matter, and roll away. If you add up mass times velocity for both carts before the collision and again after, the two totals are identical. That's momentum conservation, the thing you memorized. Now here's the Noether move. Take that entire collision, carts, track, everything, and slide it 10 feet farther down the track and run it again. Same outcome exactly, because no point on the track is special. 10 feet over is as good as here. That indifference to where along the track you are is the symmetry. And the quantity whose books stay balanced through the collision, the ledger that never changes, is precisely momentum. Those aren't two facts. The collision conserves momentum because the track has no special place. If instead the track somehow made physics behave differently at different spots, if the carts could tell where they were, then the collision would know its location, and that momentum ledger would no longer balance. The homogeneity of space and the conservation of momentum are the same statement.
Let me make sure I'm not just nodding along to something that sounds profound. You're claiming these two things. Space is the same everywhere, and momentum is conserved, are not two facts that happen to both be true. You're saying they're the same fact, seen from two sides.
That is exactly the claim, and holding on to that framing, one fact, two faces, is the key to the whole theorem. They are so tightly bound that if you told me space had a special location, some cosmic address where physics ran differently, I would tell you momentum could not be strictly conserved there, and vice versa. They rise and fall together. Now let me give you the second headline pair, and this is the one that stops people in their tracks, because it's about energy. Ask the same kind of question, but about time instead of space. Do your experiment today. Now do the identical experiment next Tuesday. Same result, yes? The laws of physics don't care what time it is. They're the same on Tuesday as they are today, the same this century as last. That's a symmetry too. You can shift the whole experiment forward or backward in time by any amount, and the physics is unchanged. It's called time translation symmetry, the homogeneity of time. And Noether's theorem says the conserved quantity that this particular symmetry hands you is energy.
Wait, stop. You're telling me that energy conservation, one of the most sacred laws in all of physics, the thing every textbook treats as an unbreakable commandment, is not fundamental, that it's a consequence of the fact that Tuesday's physics equals today's physics.
That's precisely what I'm telling you, and it deserves the full weight of your surprise, because it genuinely reorganizes how you should think about energy. Conservation of energy is not handed down as an axiom. It is a theorem, a consequence of time translation symmetry, of the plain fact that the rules of the universe don't change from moment to moment. If you want to know why energy is conserved, the deepest available answer is because the laws of physics are the same at all times. That's it. That's the reason. Energy is what's conserved when the rules don't depend on when you look. And you can feel how tight the link is by imagining breaking it. If the laws of physics somehow changed from one day to the next, if gravity were a touch stronger on Wednesdays, then energy would genuinely not be conserved. You could bank energy on the cheap day and cash it in on the dear one.
That is genuinely one of the most surprising things I think I've heard on this show. Energy conservation as a payout from the uniformity of time. Give me the third one, because you said 3 examples carry the whole theorem.
The third completes the pattern, and it's about direction. We did location, sliding through space. We did time, shifting through time. Now do orientation, rotation. Take your experiment and turn the whole thing to face a different direction. Point it north instead of east, and run it again. Same result. Space has no preferred direction. It's the same whichever way you face. That's the isotropy of space, and the operation is rotation, which is continuous. You can rotate by any angle, including a whisker of an angle. And the conserved quantity Noether's theorem hands you from rotational symmetry is angular momentum, the quantity of spinning motion, the thing that keeps a figure skater turning and a planet orbiting. So there's the trio, and I want you to hear the rhythm of it. Space is the same everywhere, gives you momentum. Time is the same always, gives you energy. Space is the same in every direction, gives you angular momentum. 3 symmetries of plain, empty space-time, 3 of the most important conservation laws in physics, paired off exactly.
That rhythm is gorgeous. Location, time, direction, and each one hands you a conservation law. But I have to ask the thing that's been nagging me. This is starting to sound almost too good, like a magic trick where I can't see the mechanism. Why does a symmetry produce a conserved quantity? What's actually happening underneath?
You're right to demand the mechanism, and the plain answer is that the full proof is a piece of the calculus of variations we'd need chalk for. But I can give you the true heart of it in words, and it connects straight back to something we already built last time. Remember, at the end of our least action conversation, we found a special case. I said if a coordinate doesn't appear in the Lagrangian, if the system's energy expression simply doesn't mention, say, the angle around the Sun, only how fast that angle changes, then the momentum associated with that coordinate is automatically conserved. We called such a coordinate ignorable or cyclic. Do you remember that?
I do. The planet orbiting the Sun. The angle around the Sun didn't appear in the Lagrangian, only its rate of change. And that instantly meant angular momentum was conserved. It felt almost like a trick at the time.
It was a trick. It was Noether's theorem in its simplest possible disguise, and now we can see it for what it is. Think about what the coordinate doesn't appear in the Lagrangian really means. It means you could change that coordinate, shift the angle, rotate the whole system around the Sun, and the Lagrangian, the physics, wouldn't notice. But that's a symmetry. Changing this coordinate leaves the physics unchanged is the very definition of a symmetry. So the humble rule from last time, missing coordinate implies conserved momentum, is exactly symmetry implies conservation, just in the easy case where the symmetry shows up as a coordinate being absent. Noether's insight was to see that you don't need the symmetry to be that obvious. The symmetry doesn't have to be a coordinate politely missing from the equation. It can be a subtle, tangled operation, some combined shift and rotate and rescale that leaves the action unchanged in a way no single missing coordinate would reveal. And her theorem still cranks out the exact conserved quantity that goes with it. She took a special case everyone half knew and turned it into a completely general machine.
So the cyclic coordinate from last time was a keyhole, and Noether opened the whole door. Let me test the mechanism with the energy case, because that's the one I most want to believe. For momentum, I can sort of see it. Slide the system. A position coordinate doesn't matter, momentum is conserved. But time translation giving energy, that doesn't look like a missing coordinate. What's going on there?
That's the perfect question, because energy is the subtle one, and it's exactly why Noether's general machine is needed, rather than the baby version. Time isn't one of the position coordinates of your system. It's the parameter along which everything evolves. So the physics is unchanged if I shift everything in time isn't the simple statement, some coordinate is missing. It's a statement about the whole Lagrangian not depending explicitly on time. The rule for computing kinetic minus potential is the same clock reading to clock reading. When you feed that particular symmetry, the Lagrangian has no explicit time dependence. Into Noether's machinery, the conserved quantity that emerges is a specific combination of the kinetic and potential energies, and it turns out to be exactly the total energy. And notice it beautifully echoes something else from last time. I mentioned the Hamiltonian, the close sibling of the Lagrangian, which comes out as kinetic plus potential, the total energy. That's not a coincidence. The Hamiltonian is precisely the conserved quantity that time translation symmetry hands you. The threads from last time and this one are the same rope.
They really are weaving together. Okay, I'm convinced there's a real mechanism and not just a slogan. Now I want to push on the profundity because you keep hinting this reverses something about how physics is done. What do you mean?
I mean it turns the logic of discovery upside down, and this is the part working physicists actually live by day to day. Before Noether, a conservation law was an empirical prize. You'd do experiments, notice that some quantity, momentum, energy, charge, never seemed to change no matter what, and you'd elevate that observation to a law. Conservation laws were discovered, hard-won, almost accidental gifts from nature. After Noether, the arrow flips. Now, if you can identify a symmetry of your system, and symmetries are often obvious, almost aesthetic, you can frequently see them just by looking at the setup, then a conservation law is guaranteed. You don't have to discover it experimentally. You can derive it in advance from the symmetry. And the flip runs the other way too, which is where it becomes a research tool of terrifying power. If you observe in the lab that some quantity is always conserved, and you don't know why, Noether tells you to go hunting for a hidden symmetry. The conserved quantity is a clue that some operation leaves the world unchanged, and finding that operation often reveals new physics.
So conservation laws stopped being things you stumble on and became things you can predict. And a surprising conservation law is now a signpost pointing at a symmetry you haven't spotted yet.
Exactly. And that signpost has led physicists to genuine discovery, which brings me to how far this idea reaches beyond carts and pendulums. Everything we've said so far used the symmetries of plain, empty spacetime, position, time, direction. But nature has other, more abstract symmetries, and Noether's theorem applies to every one of them. Here's the headliner. Take electric charge. Charge is conserved. The total electric charge in an isolated system never changes. It's one of the most precisely tested facts in physics. What symmetry does it come from? Not a symmetry of ordinary space. It comes from a subtle symmetry hidden inside the mathematics of the electromagnetic field itself. A freedom to shift a certain quantity, called the potential, everywhere in a coordinated way, without changing any measurable field. That abstract internal symmetry is called a gauge symmetry, and Noether's theorem says, gauge symmetry of electromagnetism, therefore charge is conserved. Same machine, same logic, but the symmetry now lives in an abstract internal space rather than in the room.
Gauge symmetry. That's a phrase I've heard thrown around as if it's the beating heart of modern particle physics. Are you telling me that whole edifice is Noether's theorem scaled up?
In a very real sense, yes, and it's hard to overstate. The entire standard model of particle physics, the theory of all the known forces except gravity, the framework behind every particle collider result, is organized around gauge symmetries. Physicists build these theories by first choosing a symmetry and then letting Noether's theorem and its descendants tell them what must be conserved, and remarkably, even what forces must exist to enforce it. The symmetry comes first, the physics is constructed to honor it. When they discovered that certain quantities in particle physics were conserved, that was the trail of breadcrumbs leading to the symmetries that define the theory. So the humble bridge Emmy Noether built between symmetry and conservation didn't stay in classical mechanics. It became the very method by which the deepest theories of matter are written. You choose your symmetries, the conservation laws, and much else follow.
You were careful much earlier to say continuous symmetries only, smooth knob symmetries. So what becomes of the discrete ones? The mirror reflection you opened with, do they just give nothing at all?
They give something, but something of a different character, and the contrast is illuminating. A discrete symmetry like mirror reflection, swapping left and right, does not hand you a conserved number that ticks along unchanged the way momentum does. What it gives instead is more like a rule about what's allowed and what's forbidden, a kind of parity label that certain processes must respect. And there's a famous, humbling twist buried here. For a long time, physicists simply assumed the mirror symmetry was exact, that the universe could not tell its own reflection from itself, that no experiment could distinguish left from right in any absolute sense. Then, in the 1950s, experiments on the weak nuclear force, the force behind certain radioactive decays, found that assumption is flatly false. At that level, the universe does distinguish left from right. The mirror world runs by subtly different rules. It was a genuine shock, an assumed symmetry discovered to be broken. So discrete symmetries are real and deep, but they're a different game from Noether's continuous ones.
So mirror symmetry isn't a Noether symmetry, and nature turned out not to fully respect it anyway. Are there continuous symmetries beyond your big three that I should know about?
There's at least one lovely one hiding in plain sight, and it rounds out the picture. Ask whether the laws of physics look the same to someone standing still and to someone gliding past at a steady, constant velocity, not accelerating, just cruising. They do. That's a principle as old as Galileo, that you can't tell uniform motion from rest by any experiment done in a sealed cabin. That equivalence is itself a continuous symmetry. A boost, you can boost your velocity by any amount. And Noether pairs it with a conserved quantity too. It's tied to the steady, unaccelerated drift of a system's center of mass, the fact that the balance point of an isolated system coasts along a straight line at constant speed forever. So the catalogue is genuinely richer than three. Space, time, direction, and motion all contribute. But those first three carry the whole intuition, and the rest are variations on the same theme.
I want to sit with how strange that inversion is. We build the fundamental theories by picking symmetries first, but let me turn to a worry, because you said something earlier that I can't let go of. You said if the laws of physics changed over time, energy wouldn't be conserved. That was a hypothetical, but doesn't the universe actually change over time? It's expanding. Doesn't that break the very time symmetry you said energy depends on?
You have just walked straight into one of the most beautiful and genuinely unsettling consequences of the whole idea, and I'm not going to soften it because it's real. On small scales, in this room, in the solar system, in any experiment you or I will ever run, time translation symmetry holds superbly, and energy is conserved to fantastic precision. But you're right that on the grandest scale, the scale of the whole cosmos, the universe is expanding, and that expansion means the universe is genuinely not the same from one epoch to the next. Space itself is stretching, and that means, on cosmological scales, time translation symmetry is not exact, and Noether's theorem, taken seriously, tells you the consequence you should now expect. On those scales, the total energy of the universe is not a straightforwardly conserved, well-defined quantity the way it is in your lab.
That sounds like heresy. Energy not conserved? Every bone in my body says that can't be right.
I know, and I want to be careful, because it's easy to say this wrong. It's not that energy has become sloppy, or that you can build a perpetual motion machine. Locally, in any experiment, energy conservation is ironclad. The precise statement is that when the time translation symmetry that energy conservation rests on is absent, as it is for the expanding universe as a whole, there simply isn't a single global notion of the total energy of the universe that stays constant, the way there is for an isolated system in flat, unchanging space-time. And there's a gorgeous, concrete symptom of this. Think about light traveling across the cosmos for billions of years. As the universe expands, that light gets stretched. Its wavelength grows. It shifts toward the red. This is the famous cosmological redshift. But redder light is lower energy light, so the light arrives carrying less energy than it left with. Where did that energy go? The answer Noether points to is nowhere. The question assumes a global energy bookkeeping that the expanding universe doesn't provide, because the symmetry that would guarantee it isn't there.
That is quietly staggering. The redshift of ancient starlight is the missing time symmetry made visible. And you're saying Noether's theorem doesn't just permit that, it predicts you should expect exactly this kind of thing whenever the symmetry is broken.
That's the power of it. It doesn't just describe, it tells you where to look and what to expect. And notice this is actually how Noether got pulled into the problem in the first place, which is a piece of history worth telling. Around 1915, Einstein had just produced general relativity, his theory of gravity as curved space-time, and there was real confusion about energy conservation within it. The equations seemed to do something strange with energy, and nobody could sort out whether energy was conserved in the new theory or not. Two of the greatest mathematicians alive, David Hilbert and Felix Klein, at the University of Göttingen, were wrestling with it, and they couldn't crack it. So they invited a mathematician they knew could, Emmy Noether. And she didn't just solve their specific puzzle, she went underneath it and found the general theorem, the whole bridge between symmetry and conservation, of which their confusing gravitational energy question was one instance. The subtlety they'd tripped over, that in general relativity, the relevant symmetries can be local, varying from place to place, which does strange things to global energy, was explained, permanently, by understanding exactly which symmetry gives which conservation law, and what happens when the symmetry isn't global.
So the theorem wasn't an abstract exercise. It was born solving a concrete crisis in Einstein's gravity. Tell me about her, because a name that sits under this much physics deserves more than a mention.
She deserves an entire episode, frankly. But let me at least do her justice in brief, because her story is inseparable from how science actually worked. Emmy Noether was, by the assessment of Einstein himself, and essentially every mathematician who knew her work, one of the towering mathematical minds of the 20th century. Her influence on abstract algebra alone reshaped the field for good. And she did this while being systematically denied the ordinary rights of an academic because she was a woman. When Hilbert wanted to hire her at Göttingen, the faculty objected to appointing a woman to the teaching post. Hilbert reportedly snapped back that the university was a place of learning, not a bathhouse. For years, she lectured under Hilbert's name. The course would be announced as his, and she would actually deliver it, because she was not permitted to hold the position herself. She worked for a long time without a proper salary. Later, in the 1930s, being Jewish, she was forced out by the Nazi regime and emigrated to the United States. And through all of it, she produced mathematics of the first rank, including this theorem, which quietly became one of the organizing principles of all of physics. Every time a physicist says, "This is conserved because of that symmetry," They are speaking Emmy Noether's language.
That's humbling. The sheer barriers she pushed through to hand physics one of its deepest ideas. Before we gather it all up, though, you slipped something enormous in earlier and just kept walking. You said physicists choose a symmetry and the forces follow. Not just a conserved quantity, a force. That sounds like the real punchline, and I don't want it to go by.
You're right to grab it, because it is the deepest turn of the whole idea, and it's the perfect bridge to where we're headed. Here's the move. Take that internal gauge symmetry of electromagnetism, the freedom to shift the potential everywhere in a coordinated way without changing anything measurable. So far, we've treated it as a global symmetry. You make the same shift everywhere at once. Now demand something much more ambitious. Demand that the symmetry hold locally, that you be allowed to make a different shift at every point in space, independently, and still have the physics come out unchanged. If you insist on that, something remarkable happens. The mathematics simply refuses to work unless you introduce a brand new field, a connecting field that reconciles the independent choices you made at neighboring points. And when you work out what that forced into existence field must be, it turns out to be exactly the electromagnetic field. The photon has to exist in order to enforce local gauge symmetry.
Hold on, you're saying the electromagnetic force isn't put in by hand at all. It's demanded into being, just to keep a symmetry true at every point separately.
That is exactly what I'm saying, and it's the principle that organizes modern physics. Symmetry doesn't only tell you what's conserved, it dictates which forces must exist and what form they take. Insist on local gauge symmetry for the electron's phase, and electromagnetism, the whole thing, light included, is forced upon you as the price. Insist on richer local symmetries, with more internal directions to rotate, and out come the strong and weak nuclear forces, each with its own carrier particles, each demanded by its symmetry. So Emmy Noether's bridge, pushed from global to local, stops merely bookkeeping conservation laws and starts generating the forces of nature themselves. And that's precisely why the next tutorial matters as much as it does. Electromagnetism is the first, cleanest case of a symmetry giving birth to a force, and, as we'll see, to light itself.
Let me try to gather the whole thing into one arc, the way we did last time, and you tell me where I've gone wrong. We started from last episode's cliffhanger. Physics is written in actions, and the deep prize is the action symmetries. Noether's theorem says every continuous symmetry of the action, every smooth knob you can turn that leaves the physics unchanged, hands you a conserved quantity, exactly. Space is the same everywhere, gives momentum. Time is the same always, gives energy. Every direction is equivalent, gives angular momentum. The mechanism generalizes last time's cyclic coordinates. A symmetry is any operation the action doesn't notice, not just a missing coordinate. And this reverses the logic of physics. Conservation laws become guaranteed consequences of symmetry rather than lucky empirical finds, so much so that we now build the fundamental theories, the whole standard model, by choosing symmetries first. And when a symmetry is broken, like time translation on the expanding cosmos, the corresponding conservation law genuinely loosens, which is why ancient starlight arrives redshifted and lower in energy.
That is the whole thing, captured exactly, and the sentence I'd want you to carry out of it is the one we started with, now with all its weight behind it. Conservation laws are not fundamental. Symmetry is, and conservation laws are its shadow. Energy, momentum, angular momentum, electric charge, every one of them is the visible echo of some way in which the universe looks the same after you change it. That's not a metaphor, it's a theorem, and it reframes the entire project of physics. The question is no longer only, what is conserved? It's, what are the symmetries? Because once you know those, the conservation laws, and often the forces themselves, follow of necessity.
From what stays the same as things happen to what can you change without anything happening? That's the flip. And I imagine that second question, what are the symmetries, is exactly where you're taking us next.
It's exactly where we're headed. We've now seen twice that the symmetry hidden inside the electromagnetic field, that gauge symmetry, is what guarantees charge is conserved. So the natural next move is to actually look at electromagnetism itself, how a handful of equations tie electricity and magnetism into a single field, and how that field turns out to be light. That's the next tutorial, Maxwell's equations and the birth of light. For now, carry this. Whenever you see something in the universe that refuses to change, ask what you could have changed about the universe that it wouldn't have noticed. Find that, and you found the reason. Symmetry first. Everything conserved is its shadow.
Symmetry first, conservation as its shadow, and Emmy Noether as the one who showed us the light casting it. Thank you, George. Next time, Maxwell, and how the whole thing becomes light.